All right, we'll try that again. Welcome everyone to the second session of the second day of CosmoPalooza 2023. We're happy to have the Pantheon+SH0ES team with us, our Pantheon+SH0ES team with us. And we'll get started with Dylan. So please take it away.
Hi, everyone. Okay. So we are really glad to be here. Today, we're going to talk about three main things. Myself, Adam Rees, and Dan Skolnick are all here. We're going to kind of do a bit of a relay on these three parts. The first one being the major results that have come out. Now it's about a year and a half ago from the CosmoPalooza and Pantheon+ teams. And then we'll lead into Adam talking about recent results with JWST, and then Dan talking about a very related program within this scope called CATS. I do want to highlight that feel free to grab the websites that correspond to our data releases. And also I'm going to be highlighting basically, this is a one-stop shop for questions about the CosmoPalooza and Pantheon+ measurements. So in this first part, in this overview, we're going to be basically talking about two main cosmological measurements. On the left-hand side, I'm showing the CosmoPalooza distance ladder, where the name of the game is to compute absolute distances in the nearby universe. So really only about out to redshift 0.15. And then on the right-hand side, we're going to be talking about Pantheon+, which are type 1a supernova relative distances. So they're not necessarily calibrated. And part of what the distance ladder does is to calibrate them. But in this case, on the right-hand side, we're talking about relative distances of type 1a supernovae. And in this case, we're talking all the way out to redshift 2.4, so covering something like 11 billion years of cosmic history. Okay, so just to set up some of the interest of the main thing that CosmoPalooza is tackling, and I decided to remake this slide recently because we've seen it a number of ways, but I thought this was a really fun way of showing it. CosmoPalooza, which stands for supernova H0 for the dark energy equation of state. Well, that's what its initial proposal was called. But really, the most interest on the CosmoPalooza side has come from basically what we're now calling an end-to-end test of the cosmological model. And so that's if you take measurements from the very early universe, like the CMB, in this case, we're showing basically the value obtained by Planck. You can infer the expansion rate of the universe from the angular diameter distance to the CMB. You can get a redshift of the CMB and basically back out what the Hubble constant or the expansion rate of the universe would be today under the assumption of some cosmological model that gets you to a comparison for today. And then over here, we get a measurement of the local value of the expansion rate. And that's what CosmoPalooza is doing. With this distance ladder approach in the local or nearby universe that gives us the value today. And basically the story is that these two results don't really agree with each other. So the distance ladder method, in the first rung of the distance ladder, we compute geometric measurements. I'm going to dive into those briefly. But in that first rung, we have four main anchors, three of which are outside of the Milky Way, LMC, M31, and NGC 4258. And then in the second rung of the distance ladder, in the first rung of the distance ladder, we convert the geometric calibration into a Cepheid distance scale. Cepheids are these variable stars for which we can standardize them based on their period. And we get the period luminosity relation. We calibrate that period luminosity relation to the geometric distances in the first rung. In the second rung, we transfer those geometric distances to the Cepheids, and then ultimately to the Type 1a supernovae, where we now have 42 galaxies that have hosted Type 1a supernovae and are visible up until 2021 from HST. And that was really the rate limiting step. And then out in the third rung of the distance ladder, we have many, many Type 1a supernovae out into the Hubble flow, or the cosmological expansion of the universe, where we can actually measure the expansion rate of the universe today. Where I just want to really highlight that the key to making this distance ladder work is having consistency between the rungs of the distance ladder. It's really robust. It's a really robust method against systematic uncertainties, as long as those systematics that could potentially creep in are consistent amongst the rungs. They will cancel out. And I'm going to detail that a little bit more in a second. So when it comes to the first rung of the distance ladder, there are seven sources of geometric calibration. The first three highlighted here are what we call the primary sources that we use in the main measurement. Those are the most accurate and independent measurements. So from parallaxes, specifically Gaia DR3 or EDR3. And we have water masers, that's led by Mark Reed. And then we have detached eclipsing binaries, three different methods of computing geometric distances to those very, very nearby galaxies. And we have a number of cross checks, but the end of this, the main story and takeaway here is that the three methods in the top agree with each other and are extremely precise, and the cross checks also all agree and mostly come up with very high values of H0. So the real rate limiting step in the distance ladder is that second rung of the distance ladder. And this is really where a lot of the effort within SH0ES has gone in. And we're releasing our first major update since 2016, where we're now up to 42 galaxies that have hosted Type 1a supernovae and that have had Cepheid variable stars measured. So this is really the culmination of decades of work. And really is ultimately a volume limited sample, because basically you're limited by how often a Type 1a supernova goes off in the extremely nearby universe. So the data set that was acquired since 2005, this incorporates 20 successful proposals, over 1,000 HST orbits. Is this set of Cepheid light curves that you can see here, which are then, when we compare them to their luminosities, can be standardized using the Leavitt law or the period luminosity relation, which allows us to get relative distances to the Cepheids, which themselves, for the most nearby galaxies, have been calibrated to the geometric distances. Adam is going to go into a bit more detail, especially with cross checks on this method with the JWST. So then in the third rung of the distance ladder, we have the Type 1a supernovae, and that's the data set that we've been working on for the last 5 years, called the Pantheon+ data set. This is the successor to the original Pantheon data set, which is really just a compilation of all of the best high quality Type 1a supernova surveys that have been executed over the last basically 30 years. And this amounts to 1,701 light curves of 1,550 unique Type 1a supernovae, ranging in redshift from basically redshift 0 out to redshift 2.3. You can see we're covering a large portion of the night sky in all directions. And this is the result of recalibrating 18 different surveys, which is 25 different photometric systems and over 100 filters. You can see here our recalibration covariance matrix. And what you'll notice is that because we've combined so many surveys, we actually have more light curves than we have supernovae. And that's because in the last, I would say maybe decade or so, we've had so many telescopes on sky observing supernovae that we've fortuitously had multiple telescopes observing the same supernovae at the same time, which is really great for beating down systematic uncertainties associated with the calibration of the telescopes. This now brings us to 42 supernovae in the second rung, In the third rung, we have 1,000, but in the second rung, we have now 42, which is essentially a doubling over the last analysis that we put out. And we believe that we're basically complete out to redshift 0.01, which is essentially the limit of HST. And as I mentioned, we now have an average of 2 different photometric systems or telescopes for each supernova that is in a Cepheid host. So we have roughly 78 light curves in 42 hosts. Again, really good for beating down systematic uncertainties due to calibration. Okay, so the type 1a supernovae are used to measure the Hubble constant in the nearby universe Hubble flow. That's what's depicted in this range right here. But they're also used to go out to high redshift and measure dark energy and dark matter and density of matter. And really, as a supernova cosmologist, the name of the game is to measure deviations from lambda CDM at about the 0.02 mag level, which is being depicted here, over an extremely large redshift range. So basically from redshift 0.01 or 0.02 all the way out to redshift 2 is the goal. And it's a really tall task, and we've spent a lot of our lives tackling this task. But these supernovae are also useful for measuring the Hubble constant. But from the supernova perspective, measuring the Hubble constant is, we would say, arguably easy. It's much, much easier than measuring the equation of state of dark energy, for example, where the Hubble tension being depicted here is basically on the order of 0.2 mag, not 0.02 mag, but 0.2 mag. And we're covering a much smaller range in redshift. So much less time for things to evolve and for your populations of supernovae to drift and things like that we're, of course, concerned about when measuring dark energy. But with the Hubble constant, it's relatively easier to do. So really, the latest results are basically a marriage of these 2 samples, the Cepheid sample and the geometric sample provided by CHOOS, which is really the distance ladder method on the left-hand side. And then all of the supernovae now in the distance ladder are coming from this sample, which we're calling Pantheon+. This sample that covers an extremely large range in redshift. And perhaps most importantly, and which was not the case in 2016, but now we have analyzed all of the supernovae in the second and the third rungs simultaneously. They are all coming from this Pantheon+ data set, which means we're using the same pipelines, the same light curve models, the same fitting processes, the same, we're propagating systematics across the rungs consistently. We're taking care to characterize any differences between the rungs. And this is really totally key for pinning down your systematic uncertainties and really understanding what could contribute most to systematic uncertainties across the rungs. As I said, it's the differences between the rungs that will really cause sources of systematic uncertainty. And so really what we've made a great effort to do is to propagate all of our systematics in each rung into a covariance matrix that characterizes the differences between the rungs and across the rungs, and allows you to do a simultaneous measurement of the Hubble constant, of the parameters that go into the distance ladder, and all of the systematics across the rungs all simultaneously. And so what we find in the CHOOS measurement is 73 plus or minus 1 kilometer per second per megaparsec. That is including systematic uncertainties. And that does put us at the 5 sigma level with disagreement from the early universe or Planck. You can get that significance up even further. I'll briefly mention a paper that improves on the parallax measurements. And there is a paper by Yuki Murakami that has improved on the supernova intrinsic scatter. But ultimately, this is where we stand. Now, the name of the game really has been, can we pin down our systematic uncertainties? And we've done our best effort to take the suggestions brought to us by you, the scientific community, and we've analyzed more than 67 different variants in specifically the CHOOS analysis, where we look at how this would change our inference of the Hubble constant. And this is what you can see here for many of the different systematics across all of the rungs. And really, the scatter in these is representative of our scatter in our uncertainties on the Hubble constant. And none of them really go below 72.5 without dropping some significant piece of data. Like, you know, if you only use the optical Cepheid data, then maybe you go a little bit lower. But really, Planck is all the way down here on the left-hand side. So it's just really hard to get a low value for H0, as far as we can tell, and as far as the suggestions that you've all brought to us, we really are attempting to address them, and we encourage you to keep bringing them to us, and we will do our best to address them further. So on the Pantheon+ side, the side where we go out to redshift 2.4, we have measured cosmology, the equation of state of dark energy and density of matter, critical density relative to critical density. And really, we've done a great deal of understanding our systematic uncertainties. We've actually pushed down the uncertainty floor in supernova cosmology, which has been really great, especially when it comes to looking towards the future. We've now analyzed over 100 different sources of systematic uncertainty, and we are not dominated by systematics. Our contour, the teal contour, is consistent with a cosmological constant, especially so when you combine with something like Planck, keeping in mind that this analysis I'm showing here is the uncalibrated supernovae. So it is totally ethical to combine with Planck in this scenario, and you get something that does look like lambda CDM or the cosmological constant. If we open up to evolving dark energy models, we are still consistent with 0, and it's an exceptionally good constraint. Well, not that good, but compared to other probes, it certainly is. And that's largely because we get to see the universe at redshift 2 when it was matter dominated, and at redshift 0 when it's dark energy dominated, and we get this really nice view of the universe evolving. And so in an effort to save a little bit of time, I'm going to just go through some additional cross-checks. So Adam has recently improved on the precision of parallax estimates using cluster Cepheids. These are approximately 20 of the Cepheids in the Milky Way are in clusters, from which we can get much better estimates of the parallax due to the fact that you can get a very large magnitude range of this cluster member parallaxes. This allows for a nice cross-check on the Gaia parallax 0 point. We've done a full sweep of the redshifts and peculiar velocities in Pantheon+. Really, at the end of the day, no matter what peculiar velocity map or the map that characterizes the velocities in the universe that are not from the cosmological velocity, but rather the poles of the matter field, you get high H0s no matter what we do. Although I will warn you that if you don't use any map, because the supernova sample is not fully isotropic, you do get a shift in H0 if you don't use any peculiar velocity corrections. It does shift H0 lower, but we would argue this is what you should be using these corrections. Sasha Brownsberger and I led a paper looking at residual calibration errors. These are the kinds of things that could keep a supernova cosmologist up at night. But because we have so many different samples, 18 different samples, basically any one sample or multiple samples being off in calibration doesn't really kill your H0 measurement, although it could hurt your W measurement. If you look at the scale here, H0 measurements are hardly affected. In Pantheon+, we marginalize over the potential for dust in the supernova sample at the population level. There have been 2 papers that have come out recently, Cole-Meldorf and Brody-Popovic, that have done this population modeling again and have shown that with different independent samples, this population modeling is in agreement. And then there is also a Dewan and Casey Mendel paper by a separate team that has done actual individual dust measurements for all of the supernovae and gets a high value of H0. So we don't think it's dust. And to save time, I'm going to breeze through and really kind of get, maybe this will be a good highlight for why this such a really important resource, what I'm showing here now, you can basically use this website as a one-stop shop for the cross checks that I've been just going through, the tests that have come out in the last couple of years. And we're going to be continuously updating this to hopefully show you how robust the measurements are and try to give short explainers on what's going on in each of these papers with relation to the distance ladder. We, of course, also do cover in this spreadsheet any conflicting measurements, but we encourage you to look at all in the entire scope of the cross checks on the distance ladder method and visit this link. And then lastly, I'll point you to the data products that we're making available. They're on GitHub, the Cepheid measurements, the supernova measurements, everything cataloged here. We encourage you to grab that, analyze it yourself. Our entire pipeline from end to end on the supernova side is made available, and we encourage you to dive in on that. So with that, I will hand it over to Adam. Please go ahead and share your screen.
Did we want to do Q&A for Dylan first, or should I just jump in? Anthony, you're muted.
Thank you very much, Adam. I'm not seeing anything in the Q&A right now. If someone has a quick question, they're welcome to put one in while Adam shares his screen. Maybe Adam, just get going.
Okay. Okay. Hopefully you can see my screen. Thank you very much. So I'm going to follow up where Dylan left off on the issue of the robustness of the result and how we could test it, particularly with the new James Webb Space Telescope. So the Hubble tension has been with us more or less for 10 years. It's been very persistent. It's extremely interesting because if it's not an error, then it may be an indication of new physics. So here's my sort of top 10 list of maybe most popular hypotheses that people have had over the last 10 years. I could I'll just briefly mention some of these, mostly they're covered in the spreadsheet that Dylan showed. Actually, I won't discuss any of them. I'll just say that take a look at the spreadsheet, addresses all of them, but I'm going to jump right down to this last one. Near-infrared Cepheid crowding. So this is an issue which I can describe here. Generally, we are using Cepheids, obviously, as standard candles in the near-infrared where the effects of dust are low. But when you look at a Cepheid star, shown here in red, you're seeing it superimposed through a galaxy. So the image is superimposed, the Cepheid, on top of whatever other stars are there. And so when you want to measure just the flux of the Cepheid, you need to account for the background. So you can measure the statistical level of the background pretty easily by throwing down artificial stars. And so as a result, this is not a systematic uncertainty, but it is the largest source of noise because an individual Cepheid might be sitting on top of something. It might be sitting where there's hardly anything around. And so we would like to be able to do better. And with the James Webb Space Telescope, we can do a lot better. JWST has much higher resolution, particularly in the near-infrared, than HST did. It also has greater sensitivity. And so what happens is the point spread function of all these stars shrinks to a point where you are mostly now observing Cepheids on an empty background, superimposed on nothing. And so this is a great ability to improve the precision of our measurements. So let me just briefly discuss what the different sources of noise are in Cepheid measurements. On the y-axis here is the scatter in the period luminosity relationship as a function of wavelength. So generally, we stay away from the optical if we want the most precise measurements because we can evade dust there. But we don't want to go too far to the red because you lose resolution and also the contrast is better between Cepheids and other stars. When you get far to the red, you become dominated by red giants in these galaxies. So there's kind of a sweet spot here, which is somewhere around J or H, around 1.5 microns, except Hubble has relatively poor resolution there, which produces a lot of noise. And so what's so remarkable about JWST is right in that sweet spot area, it provides really a dramatic reduction in the crowding noise. So with JWST, you're really getting sort of the best of both worlds here. And so our JWST program in cycle 1 and also in cycle 2 now is to observe 10 galaxies, which hosted 15 Type 1a supernovae, the same ones observed by CHOOS with HST, as well as the anchor galaxy, NGC 4258, that we have a precise geometric distance to. And so this completes the distance ladder and allows us to make the measurements at higher resolution. So we're using NearCam on JWST in 3 filters, FO90W, which is similar but not the same as HST's I-band, F150W, which is really the key comparison here because the HST measurements in F160W are very similar, and then a redder band, F277W. And we're making our observations in 2 epochs with JWST, separated by about 2 to 3 weeks. The value of having 2 epochs is we can confirm our astrometric identification of the Cepheid just by seeing that these things are varying over a few weeks. We can check the stability of JWST by looking at the non-variable stars, which of course are most of the stars in the frame. And as I'll talk about, we can also rephase the Cepheids. And I also want to mention another program by the CCHP team that is observing additional hosts, primarily not the ones that we are observing. Okay, so I'm going to tell you about our first 2 galaxies we've observed, NGC 4258, the anchor or an anchor of the distance ladder, and NGC 5584, which is a prototypical Type 1a supernova host, except this one has a very large sample of Cepheids, which makes it very good for comparing to HST. So here are the NearCam images we observed in 2 pointings for 4258, and wherever you see a blue dot is the location of a Cepheid. We were concerned about how stable the photometry would be of JWST because it has this complex mirror system that can go out of alignment, needs to be readjusted every few weeks. But by doing wavefront tracking, wavefront modeling, and this is done by the STSCI project, Marshall Perrin here, we saw that we had very stable wavefront over the course of our observations. You can model what effect this would have on photometry in the bands we're looking at, and generally it would be less than 1%. And again, the reference here, the Hubble tension is 0.2 of a magnitude or 20%. So this is, very, very small. So we recovered the Cepheids. Here are the color magnitude diagrams of all the stars in the fields for NGC 4258 and NGC 5584. The positions of the Cepheids are as expected in the instability strip, this sort of gap between blue stars and red stars where yellow supergiants live. Cepheids, of course, are some of the brightest stars in galaxies, which is what makes them such good standard candles for measuring distances. Here, this shows postage stamps of individual Cepheids in these galaxies. Here, showing NGC 5584. I'm showing a range of periods from about 39 to 43 days. So this is just a small sample of the 225 Cepheids we observed in this galaxy. What I really want to emphasize here is how spectacular the resolution is for JWST. So shown here are essentially the exact same wavelength, 1.5 to 1.6 micron region. And on the bottom, this is what we were previously working with, measuring with HST. The position of the known Cepheid is in the red circle. And then with JWST, where you can see so much more clearly, you can isolate the Cepheid better. And so this allows for much more precise measurements. As I said, we observed for 2 epochs, and this allows us to recover the phase of the Cepheid. So what I'm showing here on the x-axis is the period or log period of the Cepheids, and on the y-axis is the difference in magnitudes of the Cepheids between the 2 epochs. We can model this. Shown here in gray is our expected differences. So for example, when you observe Cepheids that are have a period that's exactly the separation of time we observed, then the difference goes to 0. Otherwise, it depends on where you are in phase in the Cepheid light curve. And this shows how we can match up the differences we see to the expected difference as a function of the phase of the Cepheid. So here's a Cepheid light curve showing you where you are in phase is color-coded. And so by comparing these, but we do this formally, we can solve for the phase and its uncertainty. And then the bottom line here is the ability to measure period luminosity relationships for the Cepheids with much greater precision than we could before because of the improved resolution and the reduction of any crowding noise. And so shown here in gray are the HST observations from CHO2S, and shown here in red are the JWST observations. And because we've observed now both the anchor galaxy here and a supernova host, we can look at the difference, which is the only thing that matters for the Hubble constant. And the difference here, a likelihood, is shown from the CHO2S measurements in gray and in red from JWST. And the little dotted line here is what you would have expected for Planck, meaning a Hubble constant of 67.5 using an inverse distance ladder. And so this is a very powerful check that shows a very good agreement. And so we conclude that, as I say here, that systematic errors in the HST Cepheid photometry do not play a significant role in the Hubble tension. What this graph is showing is the distance you can determine to that supernova host done in 2016 based on the CHO2S data then. Based on our 2022 analysis shown here, there's an independent group, the Arakaria project, completely independent from CHO2S, which went and grabbed the original pixels from the HST archive, used different methods and measured the distance to the galaxy using the Cepheids in very good agreement here. And then now using JWST and different combinations of band passes with JWST. All of these are quite consistent. All of these are quite far away from the Planck plus lambda CDM with H0 of 67.5. We have more galaxies that are in the process of analysis. So I'm just showing now 6 galaxies. We're seeing very similar results in all 6 galaxies, which makes that conclusion quite robust that I mentioned before. And so the overall conclusion is that this discrepancy remains quite significant. It's, as I said, lasted about 10 years. At this point, there's really no precise late universe measurement. I'm showing some of the most highly cited or most popular or most precise measurements, except in the case perhaps of lensing and gravitational waves, that are all consistently coming in above what you get from the early universe, which is also quite consistently lower from different cosmic microwave background data sets or the use of Big Bang nucleosynthesis to calibrate the early universe. We have gone through an exhaustive set of studies of systematics, variations. We don't see any internal inconsistencies or excess noise, particularly tests that have focused on hypotheses in the past about dust or metallicity or crowding as explanations seem strongly ruled out. And again, I direct you to the spreadsheet that Dylan showed. We conclude based on the JWST data that the Hubble tension is not due to errors in Cepheid measurements. So we think this remains a very interesting puzzle. Is something missing in lambda CDM? Is there new physics? This is a very hot topic, as you know, and our talk is not about the theoretical implications of it, but just the data. So now I'm going to stop sharing and switch over to Dan, unless there's questions now, and I didn't get to look at the chat.
Does anyone have any questions? Please post in the Q&A if you do. Thank you, Adam. That was great.
Okay.
Happy to take it from here.
Yeah, please go ahead, Dan, and maybe we'll do questions at the end. People, please do feel free to post questions in the Q&A if you have anything you're curious about.
Great. Thanks a lot, Adam and Dylan. So I'm going to do part 3 here. So this can be a bit of a term from kind of the Pantheon+SH0ES work, but very related. So that we're going to talk about new work on Tipler red giant branch measurements from the CATS team, which I'll explain. All right. So Adam's last slide was a good segue to this. So I think a number of people on this call have probably seen this plot where which shows that kind of have these different measurements between Cepheids and the CMB for H0. but it looks like tip of the red giant branch measurements are kind of in the middle. And so the question I always get asked is, does that mean that maybe there's no tension? And this measurement's from the CCHP team. So I kind of always wanted to look at this, and I'll say that if the CCHP team is one team, there's another team, the EDD team, extract distance database team, is led by Deep Anand. They get a higher value of H0. You could see the numbers here. So CCHP gets 69.8 plus or minus 2-ish. EDD gets 71.2. So neither of these are inconsistent. They're kind of both on the high side of Planck, but I think still people have looked at least CCHP and said, okay, well maybe that means that there's not really any tension. Okay, so the issue I think for a lot of the TRGB results is that there's just some reproducibility and consistency challenges. Like the CCHP data isn't public, and for a number for different galaxies that are measured, they're kind of unique choices of kind of how you do an algorithm for each galaxy, which makes it hard to kind of redo that analysis. So we formed this team that we call CATS. It's like comparative analysis of tip of the red giant branch. We just felt like no one could be mad at CATS. And it was formed to answer just kind of this one question, which is, can a single unsupervised soup to nuts algorithm be developed that takes in raw photometry and standardizes TRGB measurements to minimize systematic dependencies and optimize precision? And kind of the big goal is that we try to figure out what this algorithm could be and kind of release everything so that the community then could try to see if they could improve upon it. And this is not a SH0ES or Pantheon team. This kind of has some members of that, but we also have members from different TRGB teams. We tried to kind of have a lot of different expertise in this area. All right, so kind of the most important thing is that everything that we've done and I'll talk about is public. So you could, if you hear what I'm saying and think you could do better, please, that's the goal here. Take the data. You could also just take all of our code and run our detections, and all these papers have now been published. All right, so why should this be so hard? So this is what's called a color magnitude diagram. This is color on the x-axis here, and then brightness on the y-axis. And you could see that when trying to measure the tip, this is like what you can kind of see by the eye. Oftentimes it could be fuzzy. The color can move. The tip itself can be sloped. There's contamination from other stars, kind of populations. And you have to kind of smooth and do some kind of selecting, and that could all introduce biases. So there's kind of a number of different pieces to this. It's, your eye kind of sees it, but actually how to do this mathematically is not so simple. So we had this idea, which is that how do you find one algorithm that standardizes things, that kind of finds one way to measure this, and you don't have to handhold at all. And the way to do this is that there's some galaxies which have great HST data of observations all over the galaxy. Since that's the same galaxy, then when you measure the brightness of the tip, they should all give the same number. So how do you figure out the algorithm so you get the same number out for all these different observations? Because it's the same galaxy. So there's this great HST. It's called the GHOST data set that enables this work. All right, so in practice, this is what it looks like. So on the left, this is kind of where all the pointings are. And then on the right, these are the color magnitude diagrams for each of these fields. And if you just kind of take a second to look at this, you could see kind of field by field, the color magnitudes will change quite a bit. The fuzziness changes, the slopes will change a little bit. The contrast around the tip will change. So how do you do something where you kind of you measure where that tip is, so you get the same number out for all these different fields? And so it's a kind of a really fun data analysis type problem. All right, now just looking ahead, this data set that we are training on is very similar in terms of quality to the data that's used to measure the Hubble constant for tip of the red giant branch. So I'll get to this in just a little bit, but this is for all the galaxies that host supernovae that TRGB is measured for. And you can see kind of the same fuzziness, differences in slopes, and so on. All right, so the process is that you have this color magnitude diagram of brightness versus color, and you then bin this up into brightness bins, and you can or you cannot try to like take just like the red giant branch. So you can see the blue, that's some color band. So different analyses will do different things here. So you bin this, and then you smooth your bin so you're not just too sensitive to noise. And then you do what's called so Bell filter is basically like figuring out where is the derivative the highest, and that's what you can see then on the right here. So you can say where does it change the steepest? Well, that's at the tip, and you're looking kind of for the highest value here, and that's what's called the TRGB. Now, as you can see, there's a number of steps here, which is, do you put this color band on? How do you do this smoothing? How do you weight your noise? So there's kind of all these different knobs in this algorithm. So we surveyed the literature about what these different knobs are, and we parameterized each one of them, and we said, okay, well, let's vary all of them, kind of do this big grid-based search and try to figure out what does the best at giving you a consistent tip of the red giant branch value across fields of the same galaxy. So if all these different knobs, we try each one, not knowing kind of which would work. Okay, so what this actually looks like is something that is kind of messy, but there's good stuff in here. So if you look at the bottom, this is this edge detection response, and you can see for each field, there'll be multiple peaks, and that becomes an interesting challenge of how do you weight these different peaks? And on the top, this is the different magnitudes kind of. So when you have multiple peaks, you're reporting if there's two different peaks, there's two different magnitudes here. So you could say, all right, well, it's some fields will kind of give you two answers, and you have to figure out how to weight this. Now on the right here, you could smooth this more to get one peak, and then and generally that does better. But when you smooth, you could also shift the tip that you find. So what we found is that there's one parameter, we call it the contrast parameter. It's basically the number of stars above versus below the peak. It's basically the thing that your eye is seeing to say how sharp it is, and that will determine the quality of your measurement. So we could use that to basically put an uncertainty on that measurement. So this is showing kind of as we turn on different knobs, we do this kind of spatial selection. You do that color band that I was showing, and you can see just kind of how strong this R cut do. So if you say, hey, the contrast has to be so high, then you actually can really improve the precision of your measurement significantly. Okay. All right. So what we find in our training set is that we're able to reach a state-of-the-art precision for TRGB. It's at 0.05 mag scatter, and this is without any intervention, without hand-holding, having unique algorithms for every galaxy. So this is kind of the first time a number like this has been reached, and this is doing this without any hand-holding whatsoever. The other thing that we find is that this R parameter isn't just important for a quality standard, but actually the measured tip correlates at 5 sigma with this R parameter. So if we compare the residuals to the mean for our multiple fields of the same galaxy, we could see how for higher R, you get brighter residuals. And this essentially provides us a standardization routine, just like we have for supernovae or for Cepheids. Now there's something like that for tip of the red giant branch, where you could combine different measurements of different quality or different properties using this R parameter. Okay, and this is going to be really important because for measuring the Hubble constant, you have these supernova fields that have a big range of this R parameter. So if you're not standardizing over this, you could be biased towards different values of H0 because of this range. Okay, so that was kind of our first paper where we found how to do what an algorithm could be that could be where we could be kind of blind and we don't have to handhold at all. So we wrote these 2 papers, one led by Sean Lee and one by the rest of us, where we look at the different parts of how to measure the Hubble constant. So before we just kind of train the algorithm, now we're going to go ahead and use this to measure the Hubble constant. All right, so to do this, we use for our anchor, for our first rung, like what Dylan talked about in the beginning, we use NGC 4258. This avoids any reddening issues at LMC, or it's not really possible to do different distances for each star like the Milky Way. So we just use kind of one of the anchor, the kind of the easiest anchor in this first rung. All right, now for NGC 4258, we can make the same type of field plot where you see the different fields, and you can see the same problem. So, I mean, this is kind of just like asking to be used with some algorithm where you just have all these different fields, and the properties of the color magnitude diagram all look, you know, a little bit different. There needs to be some way to standardize this. And this is what this Sobel response looks like for the different fields. And you can see there's a big range of the tip values. And in the past, what's happened is there's been kind of this debate about, oh, maybe, well, like this field is better than that field. This field is more true than that field in terms of the tip. And you can see that the range of this is 0.2 magnitudes. So you could kind of make things agree with Planck, disagree with Planck, agree with Shoes, whatever, just by picking a certain field. But we felt like that's not the best way to do the science. Really, you need to standardize. You need to make that range of tips converge so that you could connect that to the supernova brightnesses. Okay, now what's really cool is that this TCR relation, this 5 sigma relation we found for these ghost fields, we find this for the NGC 4258 fields as well. So it's not like kind of this one-off thing. We also use this synthetic population code ArtPop. This is by Greco and Danieli. And actually, if you just kind of put in expectations for these stellar populations, you actually can predict this TCR relation, that the tip magnitude will correlate with this R parameter. So we have kind of multiple different data sets, as well as theory that's supporting it. And this kind of really opened up a number of new areas. So like there's this paper by Richard Anderson that showed that actually, if you look at the pulsation of stars around the tip, you could see 2 different populations. And if you correct for that, you actually can get a higher value of the Hubble constant because you're using these different populations. We also looked at the LMC, this external data set. This is led by Taylor Hoyt, and we find the same relation. So 3 different data sets, as well as theory, all showing the same relation. Okay, so we have this relation. We now know how to standardize it. We now know how to have an algorithm that we could apply to all of our CMDs in the supernova fields. And so this is what it looks like. This is what I showed before. And when we do this, this is what we get. So we have all these kind of different analysis knobs of like the color band and the smoothing parameters. And that's why we're showing a histogram, because we've found what's best for ghosts. But we also kind of want to say, what's the range of if we could have fiddled with other things? So what we get is a value of H times 73 plus or minus 1.5. And what's important here is that we're combining with the Pantheon+ that Dylan talked about for supernovae. So we checked 108 variants, and none of the TRGB variants results in an H0 less than 71.6. So you could say, all right, well, how sensitive were you to these different algorithm choices when you have those multiple peaks? So we try these different ways of doing it, where you either take the highest R peak, the highest EDR peak, the average of the peaks. So we see this range kind of from 71.7 to 75.3, with 73 in the middle. It really depends on, for that NGC 4258, if you are throwing out fields or not. Okay, now the other really important note is that as part of this analysis, we combined with Pantheon+, and when we're comparing to CCHP, they used this different data set, kind of that had older literature data, as well as just CSP supernova. And you're kind of sensitive to some of the issues that Dylan talked about earlier. So the TRGB part of this changed H0 from CCHP by 1.4, but actually just updating it to use the modern Pantheon+ data set, that changes H0 by even a bigger amount, by 2. So it's really the combination of updating the supernova data set as well as doing the standardization in an algorithmic way of doing the TRGB measurement that gives you this change to CCHP. So we feel like we can kind of trace all the way from CCHP to what we get from the combination of these 2 effects. Okay, so what did we learn? This is my last slide. So say that there's this TRGB fuzziness, and you can have multiple peaks, and this contamination normally is dealt with on this case-by-case basis, but we can do this unsupervised algorithm, which I think does kind of state-of-the-art precision, and we could then enforce it to be consistent across the distance ladder. We find that the TRGB is not kind of standard, it's standardizable, just like supernova, just like Cepheids. And you could use this new TCR relation to do this, which is supported by theory. A key part of this is actually not just the TRGB side, but the Pantheon+ side, which raises H0 by 2. So what we're seeing is the Cepheids and TRGB part of H0 are consistent. We make all of our code public, and codes that of these things that are now public. So that's EDD, now CAT, so the Anderson paper, all of the H0 values are getting higher than 71. So in terms of this question, kind of does TRGB mean no tension? I currently don't see any evidence for that, but I would really strongly encourage people to take the data that we have. It's a really great analysis problem, so we'd love for people to try to work and try to do this themselves. So stop there. Thanks.
Great.
So I think we'll be.
Thank you very much, Dan, and thank you all. Yeah, so we do have a number of questions rolling in, and if anyone else listening wants to add a question, please feel free to add it in the Q&A. People are, it looks like both Dylan and Adam are responding in text. I'll ask a few out loud. So related to your talk, Dan, does the TCR relation, this tip contrast relation, have a physical source or physical intuition, or is it just a statistical bias based on the number of stars or something?
Right. Yeah. So it's a great question. It's something that a lot of people are working on right now. I think that it's a combination of both. So I think it is physical. So you are seeing it with these stellar population codes, and there's dependency on like the age. So it's like as for older ages, you have stars moving kind of higher up the tip, so you're gathering some of that. But also there's a statistical component in that when you have a tip, you have a bunch of stars on one side and nothing on the other side. So as you kind of noise that up or smear that up with either physics or noise, you're going to have stars kind of really just jumping one way, kind of like over the cliff, and that will bias you too. So it's I think the combination of those two things that you have this age dependency, but you also have just the effect of this statistical measurement on this kind of unique distribution where you have a tip.
Great, thank you. There were a few questions that were answered in the chat, but maybe I'll ask them out loud just for benefit of the video. So Dylan, I believe you responded to this question already, but there is a question in the chat about the ACT CMB lensing analysis and the fact that it should be probing sort of more late time physics, but still gets a low H0. Would you like to address that?
Yeah, sure. I have to just go back and look at the CMB lensing.
I think that, sorry, if I could jump in, I think that is mostly a measure of sigma 8, not H0. Any H0 calibration still comes from the Planck sound horizon.
Yeah, that's what I said. And the question also asked about, BAO measurements in general having a similar kind of
also comes from the Planck sound.
So I think the short answer is that the scale is set in those kinds of measurements by the sound horizon.
Okay. thank you. And then I think, yeah, so Adam, you responded to one about sort of just various systematics, and some papers maybe indicating that a combination of them might be able to give you a large enough scatter to
Was
reconcile.
the question about peculiar velocities?
Sorry, there was two different questions and they both disappeared on me, and so I'm trying to find either of them.
If I go under answered, there was
Yes,
one
the
saying
velocity.
related to peculiar velocity reconstructions. So all the papers I've seen, or most of them, I guess I would say, that have tried to simulate large scale structure by basically taking the supernova sample, the redshifts and positions of the objects, and doing simulations from the viewpoint of the observer, like us, and looking at the distribution of peculiar velocity uncertainties that can be generated, again, factoring in that we're already correcting for peculiar velocity, would produce errors at the 0.5% level in the Hubble constant. And this is a 9% issue. So they're just, it would have to be like a 15 or 20 sigma fluctuation. So it's difficult to do. Also, similarly, people often ask, what if you live in a giant void? And the answer usually is because the type 1a supernova Hubble diagram extends to redshift 1 at least. If we lived in a giant void, as you crossed out of the void at that whatever redshift is, you'd see a kink in the Hubble diagram of type 1a supernovae, which we don't see. And in fact, there have been papers putting limits on how big it can be, and it's also about 0.5%. So I do worry if we try to get below 1% in the Hubble constant about local effects like that. But at the level of the Hubble tension, it's just not possible.
Okay, thank you. And then a question back to Dan. So Dan mentioned that after the R correction, the precision of the T RGB distances was about 0.05 meg based on the comparisons of the derived tips from different fields. Do you have an estimate of the intrinsic scatter in the tip?
Awesome question, John. I mean, from what we could tell, it seems like it may be after the standardization less than 0.05. I think we're starting to see the impact of some noise in that, so it's not as high as 0.05. So yeah, the two parts are, without the standardization, the intrinsic scatter, you'd say, is like 0.1-ish. But after that, I'd guess it's like 0.04, something like that. But you have to do the standardization.
Okay, thank you.
Right. I think, yeah, Garrett and Dylan seem to be having an interesting chat. Right. So part of the standardization is that we have to apply an algorithm to obtain the tip, and that algorithm can affect what we find for the standardization. So
I'm going to try to answer. Let's see. So Stacy McGaw asked about large-scale structure question. If we rely on large-scale structure simulations to estimate the errors it contributes, might it not be another indication of non-standard physics? Put another way, if the H0 tension indicates new physics, might that new physics lead to larger peculiar velocities and anisotropy? I think that's a fair point. I think the simulations, by and large, are assuming lambda CDM cosmology at some level. So, I guess maybe the way to say it is, in the context of lambda CDM, large scale structure, you wouldn't expect errors from the local peculiar monopole to be more than 0.5%. But, if you want to consider new physics, then I would say all bets are off. And, you could try playing with it in local large scale structure to see if you could generate something that looks consistent with the supernova data, and yet can, raise the Hubble constant. So I don't have a specific answer for, new physics and large scale structure.
Great, Thank you. And we have what might be our last question. I think it's to Dan again about the tip of the red giant. Let's see, Beaten It All 2019 didn't see the tip of the red giant variations in M101. What is the different way your measurement and theirs, or basically how do your two measurements differ?
Right. So I don't remember exactly
Actually,
what.
I do. Do you want me to jump in on this one?
Yeah, go ahead. Adam.
So actually, Beaton looked at a number of different fields in M101, and actually there was a very large variation in the tip of the red giant branch. In the end, Beaton rejected, I think, maybe 4 out of 5 fields and just used one outer field and took that as the measure. So there's no inconsistency there with what we've done with cats. In cats, we'd say, well, let's use all 5 of those fields, measure their tip contrast relation, and try to standardize them because many fields, there's only a single pointing. We don't get the option to pick amongst many. So I see those as very consistent in that sense. I just think that, it's like type 1A supernovae. You can't pick the best type 1A supernovae. You sort of have to use all of them and standardize them. And I think that's the approach here with what Dan was describing.
Perfect. Well, I would like to thank all 3 of you again and thank the whole Shoes and Pantheon Plus team and the Cats team for these excellent talks. Thank you very much. And I think with that, we can close day 2. So
Thank you. Thanks for the opportunity.
Thanks.
bye, everyone.